Hello and welcome to our TestGrid in-depth EDA demo. We'll all be going through the notebook here. Hopefully at this point you've gone through the initial TestGrid EDA notebook and have some idea about what this data is, where it's coming from, and how to collect it. What we're going to do here is try to answer a few more detailed questions about how we can actually go about analyzing this data. So as we started to look at the data in the previous notebook, we came up with a few questions, like how comparable are these test grids with each other? How can we analyze them like an aggregate to learn from their combined behavior? How many and which tests are the most common across the platform? Are their time series dates actually comparable? Is it the same for every grid? Are there subgroups that should only be compared one with another? So maybe if you look at all the grids together, they seem to have a lot of variability, but maybe there's some subgroups that can be compared directly with each other. We also want to know if looking at the grid matrices, just like the pure patterns, independent of the job or the specific tests, is a valid approach for different kind of issue identification or failure classification problems. We want to understand what is the expected behavior of tests over time and across multiple jobs. We also want to know how the entire test platform or specific tests perform on a given day. We also want to know how specific tests or the entire platform evolve over time. And all this is really to try to answer this question, is there sufficient data here and set up in a way that can be useful for applying machine learning approaches? And ultimately, do we have kind of sufficient data and sufficient understanding of the data to develop some meaningful alerting and problem identification techniques based on the answers to these questions above. So this notebook is rather in depth. I'm going to go through it rather quickly, but anyone who's interested in this, I encourage you to go to our Jupyter Hub instance on the MOC and deploy the OCP CI analysis image. There you can find this notebook under Notebooks, Data Sources, TestGrid, and it's called TestGrid In-Depth EDA. And if you go through it and find any issues or want to improve upon it, I'd very much appreciate the contributions. So cool. So let's get started. So the first thing we want to ask ourselves, right, is how comparable are these test grids? So the grids are these kind of 2D matrices that have some value in them. It's either fail, pass, or not run. There are a couple of other values, but we're not going to deal with those just yet. So it's basically three possible values that can go into each of these matrices. And we want to know if there are duplicate grids, possibly. But quickly we can see that there's 403 unique grids at the time of this data sample, and there's 403 unique names. So there's all of the grids are none of them are identical. They're all unique. However, they do have a lot of similarity in their naming convention, and sometimes the only difference is that version number that's on there. So if we go ahead and remove the version number from the naming, we then get 131 unique names out of 403. So in this case, it seems like on average, if you ignore the version, the grid is repeated about 3 times. So that may or may not be useful. I mean, we're trying to compare these things and make a statistical analysis about them. Having 3 examples of each is quite small. And again, just having the same name doesn't exactly tell us if these objects can be compared directly or not. So the next thing that we'd want to do is say, okay, the grids are really comprised of these sets of tests. So let's go and look at each of them and see if any of them have identical test sets. So we can go through and look at that. And as we go through here, we can see that in fact, where is it? It's not really clear that any of the grids share that many tests, right? So we have, for each grid type, if we remove the version number, we have between 1 and 7 individual grids. And there's not too much overlap in the tests that they actually share. So there's a couple of exceptions that we'll look at later on. But really, if we're trying to answer the question, how comparable are the grids, we've kind of discovered here that the answer is that they're not really comparable. So yeah, I mean, on average, like the largest or the average sharing test is about 20%. So that means 80% of the tests on average are unique to themselves. So if the grids as like a whole unit are not directly comparable to each other, what about the components that they're made up of, right? So we can talk about the actual individual tests. So if we just start to look at the tests, we can see how common they are and see if we can compare them directly with each other. So we can go ahead and calculate the percentage of grids that include all the different tests. Here we see overall is included in about 91% of the grids, which means it's impacts a lot of them. However, overall is kind of like a meta test that just represents all the tests combined. So it's not that informative here. However, we can see that the second most popular or like used one with 78%, impacting 78% of the grids, is the operator all images are built and tagged into stable. So it's great. So we can take this test, and so we know it impacts, most of the grids, and see how it behaves across the platform. Great. So we can go ahead and we can see that of the 403 grids that we have access to in this data set, 317 of them use this particular test. So the next thing we want to do is say, okay, so if all these grids have the same test, is it all the same time period? Are the length of the samples that we have for each grid for this test, are they the same? And when we do this calculation, we can see, unfortunately, that's not the case, right? So one of them has 118 samples, one has 15, one has 867. So there's quite a variability of the number of samples that we have for this test across each grid. So that, again, makes it a little bit difficult to kind of compare behavior of this test across the different jobs, the different grids. However, we can overcome that issue by not comparing the time series directly, but by computing some statistics on the time series and creating kind of like an object that is independent of the specific number of samples or the actual time frame that the data was generated. But again, just to give everyone a sense of what we're looking at, we can see these different time series and we can calculate the pass rate for all of them. So we have 94% passing, 93, and so on. You can just see how these different this test evolves over time on different grids. So cool. So like I said, we're going to convert this into a feature vector based on the statistical features of the time series and not compare the time series directly. So we're going to compute the pass rate, the regression slope, the regression intercept, the longest failure streak ratio, the kurtosis ratio, and the largest frequency ratio. And so I just want to be really clear here. This is just kind of as an example to show how we could overcome some of these issues. This is a little bit of like feature engineering where there's, many different ways that this can be done. And I really encourage contributors in the future to evaluate the features that I've selected here, update them, try new ones. I think this is a really good place where contributions could be really useful. So that said, I'm going to go ahead and generate these specific statistics and generate a new data frame that represents these 317 unequal time series into six-dimensional vectors described by pass rate, slope, intercept, failure streak, kurtosis, and frequency. And then we'll go ahead and visualize these as you would do. Since it is in 6 dimensions, I'm going to go ahead and use PCA and reduce the dimensions down to 2 for visualization purposes. So you can see here, just maybe some structure in the data, and then go ahead and apply dbScan and cluster the data. So here we see that the clustering algorithm has identified 4 clusters plus outliers. So there's an outlier here, a couple of clusters. So there's some structure has been found in the data. The next step here would obviously be to kind of investigate these different clusters and see what it is about the different tests that have put them into such groups and classify them, see if there's anything meaningful there. But I'm going to leave that to a later notebook. Again, this is just to kind of see if we can apply these different techniques to the data and see how we need to overcome some of the existing limitations of the data provided to us. So cool. So we did that for just a single test over across the platform. But we also want to maybe look at all of the tests in aggregate. So we can go ahead and perform the same kind of analysis for all of the tests. So here there's 117 different tests. Again, for the purpose of the demo, we're going to just limit it to about 12,000. It comes from the first 200 grids out of 400. And again, we'll compute the pass rate, slope, intercept, failure streak, kurtosis, and frequency to kind of represent our unequal length time series. And again, convert it to 2 dimensions using PCA and apply dbScan to see if there's any meaningful differentiation here. And again, it's, it looks like this is maybe not too differentiated here. There's a lot of noise, but I think this is a good place to kind of start from to identify if there's a way that we can classify the different tests based on their behavior. Cool. So the next thing that we want to do, so that we have these, we've looked at the different tests and visualized them like an individual level, but maybe we want to get some kind of aggregate knowledge about a test to define our expectation on how we think something should work. So we could want to generate a baseline of testing behavior so that as new tests run in the future, we can compare it to this baseline and determine whether or not it seems to be behaving as expected or not. So in order to do that, we can go ahead and take all the tests of the same kind and generate an average of each of these statistics. And set that as the kind of the bounds of expected behavior for these tests, so that we can compare new ones in the future. So again, that would look something like, for every test, we would have a pass rate, slope, intercept, failure streak, kurtosis, and frequency averages. And this could tell us something about how we would expect the test to run. So for this one, for example, you would say, on average, we'd expect this test to pass about 91% of the time. It does have like a small negative slope, which means, like, as we move forward in time, it's more likely to have like a not run instance. But it's such a small slope that's really flat, so that can be interpreted kind of as this, like, a really reliable test. Again, this one in particular, like, it has a failure streak of 0, so if it does fail, there's a 0% chance that it will, like, continue to fail. I guess if this was let's say it had a 5% failure streak, if it did fail, you would expect on average for the streak to be 5% of the length of the data. And then there's the failure streak. Again, it kind of gives you a sense of how often we see small flips, like kind of like flaky behavior, versus like long outages in our data. And then again, the kurtosis and frequency are just additional measures of steadiness of our time series. So this might be a really useful way to kind of summarize the behavior of test across the platform. Cool. So we can do that for many different tests, all the tests, and produce these values. And again, we can plot these 6-dimensional objects as the overall behavior of the tests, and see if there's any meaningful clustering here again. Great. So that's all great ways that we can look at the test, at the testing behavior. So we've looked at the kind of grids as a whole and discovered that they are unique enough and different enough that comparing them as kind of atomic units really is not an appropriate way to go. However, the grids are comprised of tests, and the tests are in fact kind of repurposed a number of times throughout the platform. So we can take the tests as a unit to analyze, and because they have different samples and different time series, we can use these statistical methods to convert it into some kind of object that we can do analysis and machine learning and visualization with. So the next thing that I want to talk about is how some claims that we could make about the platform on a given day. So we've kind of looked at the horizontal perspective of a grid, if you will, like cutting across the grid horizontally, looking at specific tests. Now we want to like cut it vertically and see how it behaves on a specific day or for a specific build. So we can go ahead and get some values about that. If we go here, we can say that given the day that we were interested in, the entire platform had like a 61% pass rate. So great. I don't know, maybe that's good, maybe that's not. But I think that's a key performance indicator that somebody who's monitoring the platform would want to know, and seeing how that number changes over time could be useful. And so now that we know how to collect that number for one day, let's go ahead and collect it for all the days that we have data for, and see if we can kind of map how the pass rate for the entire platform shifts over time. So we can go ahead and do that and plot that, and we can see from September 1st to September 25th, we had a platform pass rate that went from about, I don't know, 57% up to 86% or so, and kind of fluctuated between there. So it seems to be somewhat stable around maybe on average 70% pass rate. But monitoring this over time and pushing it towards 100, I think would be a good way to think about how to improve the CI platform over time. And so this is obviously the platform as a whole, but there's many kind of subgroups and sets of tests and platforms that kind of make up the whole the whole platform. So maybe you don't really care about the platform overall, but you want to look at just a specific test or set of tests and how they operate over time. So we can do the same thing here. And again, we have this plot where we're looking at the average or the percentage of pass rate and the actual count of tests that were run for each day. And we can see for this one, there was some interesting drop on the 9th, but for the most part, it's been around 97% or 97% pass rate. Cool. So now we've looked at the kind of the horizontal slice of the data and the vertical slice of the data. And those are two interesting and valid avenues of exploration of the TestGrid data. But there's one kind of special quality of the TestGrid data that we don't want to overlook, is that it really is a 2D array. So we can also kind of take the grid independent of the test names, of the build dates, and just kind of take the patterns that are being generated by the grid and see if we can find anything meaningful here. So for example, there is a particular annotated image of a test grid that was done showing how some of the different patterns that can occur are representative of different types of errors. So there's infrastructure flakes, flaky tests, install flakes, and new test failures. And they all have like unique patterns. So ideally, this is something that we could potentially apply like a convolutional neural network to, or some kind of machine learning approach. But in light of, or in absence of a lot of like labeled examples of this kind of thing, we can use some basic heuristics and some kind of signal processing handmade convolutional filters to solve this problem as well. So we'll create a filter that will try to identify this type of infrastructure flake by having these diagonal failure patterns that we want to identify. So we can go ahead and apply this. And this is kind of like a grid that indicate the black values indicate where the convolutional filter was activated the most, and indicates places where some of these infrastructure failures are most likely to have occurred. And we can go through and we identify that on specific dates we have some likelihood of these infrastructure flakes occurring, and in fact they did. So cool, great. So again, this was kind of more of a in-depth exploration of the TestGrid data to see if we could answer a few questions to move this project forward. So namely, how comparable are the TestGrids? I think we have come to the conclusion that the TestGrids as they stand really aren't comparable on their own, unless we just ignore the test names and the actual time frame, but just look at the pure patterns. Otherwise, we're going to have to break it down into the individual tests, or looking at specific dates and builds. And there are also methods that we can do to take this data, convert it into kind of compact like 6-dimensional or n-dimensional objects that we can start to compare. We can also look at how the platform behaves on a given day, and how that can kind of evolve over time. And as far as, is there sufficient data here for ML approaches? I think there's absolutely enough data, especially if we focus on the level of individual time series for tests. I think there's about like 117,000 time series across all the tests. Great. So I hope this was interesting and insightful and helpful to anyone who's interested in contributing to the AI for CI project. And hopefully you have a better understanding of the TestGrid data, what is there to be analyzed, and kind of what some of its limitations are. And hopefully you learned a couple of ways to overcome some of those limitations. So as always, I encourage you all to go to our repo, contribute to this notebook, issues, comments, whatever you think is appropriate. And I really look forward to getting some feedback. Thanks so much.